Okay, so last class we discussed about program binaries. We also discussed about how flaws can be introduced when we are writing programs. Either it could be through humans or bugs. We understood that when we write a C program, there are two different versions of an object file which is created. Either it can be looked as an executable view or as a linker view. We also saw that if we want to just understand the content, we can write certain functions and certain commands just to get what exactly is stored in this ELF files. We also discussed if we want to see if you want to just look at when an executable is created, then in that case, there is a header and we also have sections and segments. During the executable view, we have a linking between section and some segments. So there were certain commands that I wrote last time. If you remember, this was -h is used for getting the header file information. Then -s is used for getting the section related information. We saw that whenever program is written, there is some symbol table which is created. There is some program bits and other kind of other information. Some are writable, some are just executable in nature. We also discussed that if we want to look at the executable view, then in that case, we would be able to look at the segments. So we saw that if we want to look at that, we can use -l command for this object file that we created, which can be used to see the linker view, executable view, which links between the section and the segment. We saw that if we use this command called a objdump command, we can get the machine code as well as the assembly code, which is related to this hello function that we have written in C. This is compiled on a 32-bit machine, and this has been compiled on a 64-bit. So EBP gets replaced by RBP and RSP. Then we saw that as soon as a program is executed, a stack is created, and the content of the stack is from a higher memory address is reduced to a lower memory address. We also saw that we can find the function, the process ID which is created for a specific object file, which is 2552. In this particular virtual map, we can see a heap is created, and there is also a stack which is dynamic in nature, and that has a specific value of zeros. We also saw that we have two pointers, which is termed as base pointer and a stack pointer. Initially, base pointer and stack pointer are at very high, at the same position, and stack pointer gets reduced. And after that, once you complete a particular function call, the base pointer position goes to the next function call, and it copies the previous base pointer position, and the stack pointer gets further reduced, and then we will have local variables. If we want to execute a specific function, then in that case, it will just reverse the process and it will pop. From a lower memory address, it will go to a higher memory address. We saw that if an attacker comes into picture, then in that case, what an attacker can do is that instead of going to a return address, which is returning to a specific location, an attacker can change that return location to a specific other location, which will either go to a specific code or an address location, which is performing some kind of an attack. So that's how an attacker does. So what it does is that there is an expected flow of a program. An attacker will understand what exactly in this program is going on, and it will try to identify a place or a position, and specifically it will try to find a position wherever there is a return address, rather than going to a return address, it will go to some kind of other memory address which will execute the payload which the attacker wants to do. So we covered all of this. We also covered this particular program where we were inserting these values, which was, so let me show this. Here in this case, there were three values, which was 3, 2, and 1, which was initially inserted. There is this buffer 1 and buffer 2, which is total taking 16 values, which can be represented in an, I think here is that code. 1 second. Here in this case, if you will see, the 3, 2, and 1 is stored in the stack. So this is the function called 3, 2, 1, which is stored over here. Initially push base pointer, push the content of base pointer to a stack pointer, then subtract certain values for the stack pointer to insert 3, 2, and 1, then call the function which is at a specific location, which is over here. In this case, push base pointer and stack pointer, and then subtract stack pointer to store 10. 10 is the hexadecimal version of 16 values, which are in this buffer 1 and buffer 2. Then after that, we saw that as soon as we call this, let's come over here. Here in this case, this is one, a very hypothetical example where, let's suppose if you have an address location which is starting from 1000. Initially, when you pass 3, 2, and 1, they get stored. And right now, each of these integer values are taking 4 bytes. So we will have these stored in the form of 4, then 4, then 4. Then after that, we will store the return address, which is mentioned over here, which will again take 4 bytes. Then we will store the previous base pointer value, which is again stored. Then what we are doing is we are allocating memory of buffer 1, which is of 5. So 780 to 976. Once again, if you will see, the memory address is getting reduced from a higher memory address to a lower memory address. Then buffer 2 is taking 10 bytes because of these 10 values. So 975 and 66. And stack pointer then comes to the 60 of 4. Now, if you will see that if we will access buffer 2, which in this case is 966, but if I will do buffer 2 10, then it will add 966 plus 10, which is 976, which is belonging to buffer 1. So here what it is doing is that the range of buffer 2 got exceeded to a specific value where buffer 1 was present. And that is what is termed as buffer overflow. And that was the first initial attack that happened on program binaries. So we will understand how this works as soon as I will run my Linux machine using GTB. So if an attacker comes into picture, what an attacker can do is that instead of going to this return address, which is specified over here, which is like, let's suppose you process this function and you store these values, but instead of going to this return address, an attacker can change it to some arbitrary location. So if I want to access a specific location, what I can run is that I can use buffer to 19, which is 66 plus 19, will lead me to a return address position, and it is expecting a return address. But rather than specifying that return address, an attacker can take it to some arbitrary location where this the program execution will no longer be part of the stack, but to some other location. And this is how an attacker can subvert the execution, which is how to break a specific flow of program to a specific other location. Once you will take the program to some other location, the next step that an attacker can do is to execute the payload. And how exactly a payload can be executed is illustrated in next consecutive slides. So here, if you will see, is that instead of going to some um, uh, um, the return address, it is going to some arbitrary location. And there in that arbitrary location, what an attacker can do is can introduce some exploit code which the attacker wants to introduce. And once this exploit code is executed, rather than going back to the function call, it will again go to the buffer address. So what it will do is that again, once you have executed, it will again point towards the buffer address location. So it will come back to exploit the code once again. And next, once again, it will just continuously, you will provide buffer address location, which is taking to the exploit code. And this kind of an attack is a buffer overflow attack where you change the position to somewhere else, and that particular position has an exploit code, and after that exploit code is executed, rather than going to the normal processing, it will loop back to again exploit the code once again. So how a payload can be executed or introduced in from an attacker's perspective. I'll go through step by step so that you understand how what is the basic mindset, and if you want to be some kind of an hacker, how you can introduce some uh, exploit code inside your own program. So let's suppose the attacker wants to spawn a shell, like he wants to execute a shell as soon as the program is run. It should, rather than going to the normal processing, it should be executing a shell. So what an attacker will do, the very first step is he should know how to create a shell. So this is some basic function which is creating a shell. So the attacker will write a specific code in C language. The next step, once he has written that particular code, then the next question comes in, how will he put this onto the stack? And how he will put is that code that he has written, he will identify, he will get the machine code associated with this. So does anyone remember how to get the machine code? For a specific command, if you remember, I explained in the class how to get the machine code. Yeah, obj dump. So here in this case, he will just write the obj dump command, disassemble all, and he would be able to get both the assembly code and the machine code. Now, if if the command, if that small function which has been written is shell code, so shell code dot object file, and then disassemble all, and then get some machine code which is listed over here. So this is that machine code. So it will copy that machine code. And then next, one more thing these sometimes these attackers do is that rather than using zero zeros, they will change these 00 values to some other values, just to so that you will no longer be able to have access to the code. So they replace it with some other instruction. So once you get the machine code, the next step is that you find a location where you can introduce this specific machine code. So let's suppose you have some program which is taking a last string, which is 128-bit. There is another buffer, which is again 48-bit. And here what you are using a string copy function where you are taking the last string value and you are copying this value to a buffer value. So in this case, this particular str copy function can be a cause of buffer overflow. And how it can be a cause, we will see. So let's suppose you got this machine code associated with this. So when you are expecting, so let's suppose this was the shell code, which is this entire string which you got, and this was the last string, and it is expecting the user to give some input. So here an attacker can input this shell code to be written on the last string, which is taking this last string value to be copied to that other buffer value, which is just 48. Once that is being executed, that shell code is executed, the next part that he is doing is that he is providing the buffer address, which will again execute this shell code. So again and again, this buffer address would be executed. So once that buffer address has been executed, it will go back to executing the shell code, which would be the address of this BA for this buffer. So now in this case, if you will see on the stack, as soon as you took this last string value, which you are taking as an input from the user can, pre-assuming this user who is using this code is an attacker, can introduce this shell code, and this shell code would be introduced in the buffer, which is stored, which is taking values from a last string value, and again, this shell code would be executed. So when str copy returns, the exploit code would be executed rather than the actual code that needs to be executed. So the final state of the stack would be just replacing it with that exploit code, and instead of going back to its normal address location, it will just execute the buffer address location. So this is some kind of small function which is written where you are there is a shell code array which is just executing a shell, and here is this str copy command which is taking a last string value and is inserting it to the buffer, which will be exploiting this particular shell code, and a shell would be created. So the very first particular buffer overflow attack which came into picture was termed as Code Red, and that was released on 13th July 2001. And there were nearly these many computers that were infected. This particular figure looks very much like COVID, because in COVID also, if you remember, there were so many websites which were showing how that was being infected. So it's not the people being infected. In 2001, it was the number of computers which got infected. And the way this was done was that it was, this was the string which was used to input the shell code, and as rather than executing the normal code, it was giving a kind of a command prompt which says that welcome to this particular worm.com and hacked by Chinese. So it was just continuously giving that continuous command prompt rather than the actual normal functionality. A lot of computers were wasted. So the way we can add on some kind of defenses is using canaries. But before I introduce and tell you how exactly canaries work, but let's first see how exactly these addresses are basically seen on Unix machines. Let me run certain commands. I have shared bunch of C files with you, and I want that you try those files to run it on your machine and see how the addresses are being updated. 1 second, it's getting opened up. So any questions so far? Oh, I didn't know that. Okay, so there are some particular C files that I have given, and let me just to go. Downloads. So I have the examples that I have uploaded is, I believe, example 1, test code, overflow, and these commands. Let's try first with example 1, that what exactly this example 1 is showing. So let's see. I'll open example 1. So this is the same function that we saw, that it was using the main function, which was using, which is calling this function, which is 1, 2, 3. And when it calls, it goes to that function, which takes in two buffer values, which is buffer 1 and buffer 2. Buffer 1 is 5 and buffer 2 is 10. So we are aware of what this function does. Now let me compile this particular program. I will not be compiling it through a normal way. I'll be using certain commands, and all of these commands are mentioned in the write-ups that I have provided. But if you want to try along with me, feel free to do it. So the very first thing you write is GCC. Then we will be using this command, which is fno stack protector. The reason we are using this is because, as I mentioned, once that attack happened, there was a defense mechanism which was utilized in order to prevent a malicious actor to modify certain location. And if somebody does, canaries are enabled so that nobody would be able to modify that particular location. So if you want to disable that functionality, and that's what we are using, this particular command, that I do not want a stack protection. So fno stack protector just says no stack protector, then -z execute stack. Just execute the stack as is without any stack protector. Now, besides this, I'll also use this command just to compile it on a 32-bit processor. Mine is a 64-bit because it gives RBP and RSP. I'll give one example just specifically on a 64-bit and one on a 32-bit processing, which will give you EBP and ESP value. So here I'm just specifying that, and then I'm using this particular command -G to execute the symbol table. So I should be able to see the symbol table, and I'll tell you what exactly is a symbol table. But that -G would enable me to see the symbols being updated in how exactly the table is being updated. So -G is used after that, and then I'll write example1.c followed by -o object file, and then this is the name of this example1. So very long command. So I've compiled my example1. Now, what I can do is, if you remember, object dump command was used to just to get the assembly code -all example1, then example1.lst. And I can see using this cat function. Let me just open a new terminal. So I am just opening this example1.lst. Okay. So if you recall, there is a bunch of machine code and assembly code, and I'll go to my main function. So my main function is where? Okay, here is it. So if you will see over here, the very first one is push the base pointer, then move the base pointer to the stack pointer, then call, and then I'm moving the, and here if you are seeing, it's since it's compiled on a 32-bit, I am able to see EBP and ESP. Then I'm pushing 3, 2, 1. Remember that function which was using 1, 2, and 3. So 3, 2, and 1 would be pushed, and then call this function, which is this located at this memory location, which is 8049176. So as soon as these three should be executed, after in my stack, I should see this return address, which is 80491A09, which is just after that call function. And that's what we will be seeing. So I'll go back to my previous terminal. Where is it? Yeah, here. So now I'll use this GDB, which is a debugger or a tool which is used to look at the memory addresses, how exactly this has been updated. So I'll use this and I will pass on this example one, which is that object file which I have created. So I'll run this over here. And if you will see, I'm getting this one, which is termed as, I'm reading this as reading symbols from example one. If I do not use this a particular -G in my command, I would not be able to read the symbols. So that's one thing that you should always keep in mind and try to run your program by not including -G, and you would be able to see that no symbol tables, no symbols loaded from example one. That's what you would be seeing if you will not use that -G. So first of all, I'll just list. So it will list the entire program that has been written, which is this function, which is taking ABC, buffer one, and all these, and then main function. So it listed down the entire code over here. Now, B is used to assign breakpoints. For those of you who have normally in debugging, in MATLAB and everywhere, we use this breakpoints so that the program should run till that breakpoint and should wait till the time further action is given or further anything is given. So I'll put a breakpoint at 10. So if you will see, I get that breakpoint 1 at a specific location, which is example 1. So I get that particular breakpoint has been assigned. Then after that, I will use this run command. R is used for running. So it will run this particular program and it will stop at this line location, which is 10 in this case. So it will stop over here. So I'll run this and I see that the program has been started and breakpoint 1 has been assigned, which is at a specific, which is function 123. So all this is good. Now, next, there is another command which is called as info registers, which will give me the information related to the registers which are present. So here in this case, we would be interested on 3 register. One is the instruction pointer, which will tell us where exactly the program is. Base pointer, if you remember in a stack, initially a base pointer and a stack pointer are a specific location, and after that stack pointer moves. So we are also interested to understand where exactly the stack pointer, base pointer are initially when the program is run. So I will use EIP for instruction pointer, EBP for the base pointer, and ESP. Once again, it's a 32. I have compiled this as a 32-bit. That's the reason I'm passing this as EIP, ESP, and EBP. Now, if you will see here, I'm seeing that the instruction pointer is at a specific location and both base pointer and stack pointer are at the same location, which is right. Now there is another command that you can use is disassemble, which will give you where exactly is your instruction pointer, which in this case is pointing with this, which is the same thing which we saw in the other, no, you can change the position. You can write ESP and with different order. So here, this is the current instruction pointer, which is over here, which is right. The same thing we were able to see in the other terminal. If you saw the other terminal, where was it? The terminal. Yeah, here. In this main one, also it is the same one, which is somewhere over here. Somewhere over here. That's where I am able to see it rather than going to on your obj dump. I can use this command called disassemble. So I'll go back to my terminal which is this. Where is it? Sorry. Yeah, here. Yeah, so here is this where my instruction pointer is. Now what I'll be doing is I will be using single instruction to execute certain stack values. So what I'll do is I'll use SI is the command which is used to execute a single instruction. So SI. Now, if I'll do disassemble, just see now the single instruction is from this particular location, and 9E, which was pointing towards 3. Now it is pointing towards A0, which is it has executed a single instruction. If I want to look at the contents on the stack, which is both base pointer and stack pointer, once again, I can do this info register EBP and ESP. You will see now stack pointer has moved 4 bytes because 3 has been inserted. And now let us also see the actual contents of this stack. So far, the memory address has been updated, but we also want to look at the content of what exactly is stored on this stack. So there is this command called x32x. So x is saying that I want to check the content. 32 is the memory locations I want to access, and x is represented in the hexadecimal format. Then after that, I'll use dollar and then followed by ESP, which is I want to see the content of stack pointer and illustrate these 32-bit of information. So let's see what exactly is seen over here. So if you will see that our stack pointer is at this location, 0xFFFD164, which is over here, which is storing 3, which is what should be there because we just executed this command. And this is the stack pointer, and 68 should be somewhere over here. We will also check one more, no, not right now. We'll check it later. But now let me do one more single instruction and see if 2 gets added. Just let's see. So SI, once again, disassemble. And 2 is being executed. Once again, I'll use this command x32x ESP. So you see that now I have 2 being added over here. Once again, I'll do single instruction and let's see 3, 2, 1 are added. Next thing what we would do is let's do disassemble and see that now it is calling this function. And if you remember, when we saw that when the locals of a functions are locals of this main function is introduced, the next thing what we do is we add the return address. So the return address is just after whatever is being executed. So let me go back to the slides and over here, let's see over here. So if you see that the way it stores is that we have parameters for function, which is over here. And then we have the return address. And this return address should be just a line after this function 123, which is somewhere over here. So I'll go back over here. And this should be stored as the next value. And let me do a SI once again to just see if that gets stored or not. So I'll do SI. And 3 to 1 has been added. And let's do again x32 ESP. So see, this is a 0x080491109, which is the next return address which is stored just after 3 to 1. Is everyone following up? Is the pace good? Am I too fast, too slow? It's very hard during online class. Well, it is even hard when I teach in person because you guys don't talk. But is everyone following up? Oh, it's a little faster. Um, okay, I'm recording this lecture, so you should be able to look back again on this recording. So if I'll be a little bit slow. Um, Yeah, the commands are a lot, but once you run a certain C programs, you should be able to see what exactly these commands are. But I'll be slow. So what we are doing is we inserted 321, and after that we are storing. We use this command single instruction so that the instruction pointer will be calling this function, which means the next thing that the stack needs to remember is once it calls the function, where exactly it should come back. And in this case, um, okay, it's a little faster. Okay, okay. So let me be little bit slow. So here, then once this function is called, it should return back to this next address location. So as soon as single instruction was called, it is calling the function 1, 2, and 3, and it is also storing the return address, which is the next value, which is over here. So far what we started with GDB compiler. Just to refresh you, we started with our GDP. We initially wrote this command to have no stack protection, to execute the stack, and also use a 32-bit machine. Then we use this command just to disassemble and see where exactly the contents are stored for main and function. Then we use the GDB command to run the object file. Then first we use list to list down the entire program. Then what we did, we assigned a breakpoint at 10th location, which means that the program should run till line number 10. And after that, it should stop till anything else has been given from the user. So we assign breakpoint 10 and then we run the program. So as soon as we ran, we saw that the breakpoint was assigned at 1, and now it was at function 1, 2, 3. The very first command that we wrote was info register EIP, EBP, and ESP, just to know the memory addresses of where exactly instruction pointer is there, where is the base pointer, and where is the stack pointer. So here in this case, the instruction pointer is somewhere over here, and both base pointer and stack pointer is at the same location. And we have seen in the slides where I have mentioned both stack pointer and base pointer are initially at the same position. And after that, stack pointer moves. And it moves till the time the entire function has been executed. And as soon as the function is calling something else, then the base pointer and stack pointer would move further down rather than just stack pointer being moving. So what we are using next command is disassemble, which will just give us how exactly and where exactly the instruction pointer is. So here in this case, we saw the instruction pointer is at this location, and we can verify that this is over here, which is right now wants to push this 3 value because function 1, 2, 3 is there. So 3 would be pushed first, then 2 would be pushed, then 1 would be pushed, and then we are calling this function. After that, we should be storing this return position. But right now, since we are over here, and since we have assigned a breakpoint, we are using SI, which is a single instruction, to go towards next position. So since it is over here, the next thing I want to do is to go at this particular position. So I'll use a single SI instruction. So it does SI, and if you see, I see this has been updated, which means that earlier it was over here, which is 19E. the next, this should be executed, and that's what it is doing. It is executing this, which is just next to this function. Okay. After this, I again do disassemble to just verify where exactly is the instruction pointer, and there it is, which is over 2. Now, I again used info register EIP, EBP, and ESP just to see if the instruction pointer is updated and base pointer and stack pointer is updated. So instruction pointer got updated to this particular position, which is over here. Base pointer is still at the same location, which was the same location, 168, but the stack pointer got updated 4 bytes because we added 3. Then we use this command x32x $ESP to check the contents of this stack pointer. Since it is starting from 0xFFFD164, that's what we are starting with this. And since we used a single instruction, so 3 got added. Next, we use single instruction. It gets updated to the next location, so which is over here. So it got updated to this particular location. So we used again disassemble, and we saw that it has been pushed. Next, we used x32 ESP. So we will have 2 being added. Again, SI, next 1 would be added. Then again disassemble, and we saw that 3 to 1 gets added. Now it has called this particular function. After this, we used a single instruction. So it is actually now calling that function 1, 2, 3. But after that, we are also checking if the return address is shared or stored or not on the stack. And it is stored because just after that, after the calling function, which is this address, gets updated on the stack, which is 0x080491A9. Any questions so far? Okay. So now, once we have done this, what we can do is again, maybe let's do single instruction once again. So let me do single instruction just to check if it gets updated. So let's do info registers first. Do info registers and EIP, ESP, and EDP. So this is instruction pointer is no longer at any of these locations, but now it is 8049, which is the function, which was that function. Remember in the disassemble, we can see over here, disassemble, this one was 08049,176, and that's what we are seeing in our terminal, which is this, which got updated over here, because now you are at that particular function. If I'll do disassemble, so here I am at the end of the register, but I will use disassemble function. I'll do disassemble function, which is at the same one. So what I'll be doing, since you remember that these were the 3 commands, which was storing buffer1 and buffer2. Buffer1 was 10 or buffer2 was one way or the other. Let me go back. So it was 5 and 10, which means total of 16, which in hexadecimal value is 10. So I'll go back to over here. So if you see that stack pointer needs to be updated and further shifted to 16, which in this case is your 10 bytes, which are got 16 in hexadecimal is 0x10. So this gets updated. This got subtracted. Now what I'll do is I'll do single instruction 3, which means what I'm doing is that I want to do three instructions together. So SI3 means 3 instructions would be executed. So I'll do SI3 over here. And now let me do disassemble just to see where exactly now we are. So if you will see that it has now it executed these 3 steps, step 1, step 2, and step 3. And now the instruction pointer is over here, which is 0x084917, which is over here. Uh, now what I'll do is I'll do x32x and dollar ESP. So if let's see where we are exactly. So we saw it was 3, 2, 1, the return address, and then 0xFFD16, which gets updated, which is some like garbage which has been added, which is this 0xFFD168. Now what I'll do is I'll do again info registers, EIP, ESP, and EBP. Info register. And now if you see, both stack pointer and base pointer are at the same location, because so far I have not added these bytes. That is the reason I'm seeing both of them at the same location. Now there is also another command that you can use, which is called as info locals. So info locals tell you, if you call a specific function, what exactly that function has. If it has local variables, what are the local variables? And since we are at this function, we can use info locals to know what exactly the local variables of function are, which in this case is buffer1 and buffer2. So if I do this, you will see that buffer1 has some garbage data, and buffer2 has some amount of data, garbage data. So info locals would tell you the names of the local variables related to that function. You cannot use this function if you are in main. You can use it when you are calling a particular function. Then there is another command which is very important, p-x and address of buffer1. So what I am interested right now is to know what exactly the address of buffer1 is. So if you will see, this is the address of buffer1, which is 0xFFFD14F. If I want to know the address of buffer2, I can see that as well, which is 145. So PX dollar buffer1 and sorry, not dollar, M% buffer1 and buffer2 will give you the address. If I want to know the content, I can use P-X and just write buffer1. So it tells me that buffer1 has 5 bytes. And if you see, this is some data which is being stored, which is 5. If you remember, buffer1 was just taking 5 values. If I want to do buffer px buffer2, I can get these 10 values, because it is storing an address, a total of 10 blocks of values it would be taking. Then if I'll do single instruction once again, and let's do x32x $ESP, we will see 321 gets added, then the return location and some other data which gets added. And this is related to that function, and function has some arbitrary values. And that's the reason we are getting all of these values. Once again, I'll do SI 3, and it is still at this function. And let's do S32X. So three further after 321, 3 further things have been added besides those original values which were there. And I can further debug this particular program and look at where exactly I am. So disassemble. Okay, so now everything is done. Only these three commands are left, which is nope, leave, and return, because it has executed, it has inserted, this subtracted this 10 bytes of values, this has added, and finally I can do info registers and EIP, EBP can be installed. And if you see that now our stack pointer is over here, our base pointer is at 54 and stack pointer is at 44. So these are some bunch of information which gets added um, when that function call was being executed. So these are some of the instruction that you can see and understand and just see what exactly the program is doing once the entire code has been executed. So we covered single instruction, we covered x32x, we covered info locals, px, and other kind of commands. Any questions so far? No, so 0x is just the address location. Right now, we haven't introduced any kind of vulnerability. 0x just specifies address location. Uh, uh, RSP and RBP, that's what you are saying? Or what was I didn't get what R? Sorry. Oh, R command. R command was for running, to run the command. So this was an example for a 32-bit. Now let's see if I want to do it for 64-bit. And I think I have uploaded that one too. So if you do not want to use this 32-bit and if you are using a 64-bit processor and if you don't want to use that original um, that entire code, what I will be doing now, right now, will be using this test code command. So this is testcode.c. And here, if you see, this is where some kind of vulnerability could happen. Can anyone tell me why a vulnerability can happen over here in this particular program, if you understand this program? You can unmute if it's better. SI is used for single instruction. So wherever is your instruction pointer, SI will just move your instruction pointer to the next address location. It will execute a single instruction wherever you are in the stack. Is it possible the argument passed string could be greater than 10 bytes? No check for, yeah. So here in this case, some vulnerability can happen because first of all, you are expecting some input from the user. And if you remember, a buffer overflow can happen when uh, due to the human factor, as well as if there is a vulnerable point. And the vulnerable point over here is this str copy. So you have this buffer which is 10 and you are copying the content of string which you are taking from the user, which the user can have a very long string, and we are copying into the buffer, and buffer could be at somewhere some location which will be having some limited size which is 10. So if the string which is being passed is very long, it can just override the buffer and that string could be manipulated. So buffer overflow can happen over here. So I'll go back and let's run this command on a 64-bit, which is my actual one. And this time again, I'll use GCC dash FNO dash stack protector. Once again, we are doing the stack protector. to disable the canaries so that we can see if the actual contents are stored. Dash Z and then execute stat and then test code. Sorry, I want to run the test code command. And then after this, this is testcode.c. But before that, I will also use dash G. Dash G to, let me do one thing. Let me not introduce this dash G first of all, and you will see why it was important to introduce. Then dash O, and then test code dot, oh, sorry, test. Isn't this test code in my, let's see, test code is this. Did I mess up some command? Let me just verify. 1 second. I'll again say that GCC FNO stack protector. I did add a space. Let me check. Execute stack test code dot C. And let me just compile this. Okay, I'm not creating an object file. So GCC FNO stack protector dash G execute stack and test code C. Now, if I want to do this GDB, I can just have my object file, and you will see no debugging symbols found in this a.out. And if you remember, the reason we introduced this dash G command is to have that symbol table ready. So this will not work. So that is the reason we use this command called dash G, which is dash G, and then testcode.c. Once again, I'll try dash O and then test code. I think this should work. Okay. Yeah. GCC FNO stack protector dash G test code dash O and test code. Okay. Now let's go to GDB and then test code. Okay, this time I'm seeing the reading symbols from this test code. And now let's do list. And I see the entire program which is written over here. Now let me assign a breakpoint at 9. Okay, so breakpoint 9 will be just taking the contents by running the argument by running with some arguments which I will be passing. So I let me since it is asking for some input and buffer is just 10, I'm inserting more than 10 values, which in this case is some large amount of values. So here in this case, if I see that it assigns a breakpoint, and let's see if the contents are being copied and how exactly the contents are being copied. But before that, I'll also assign a breakpoint at 5 just to stop the functionality over here, that string copy. Okay, now I'll use info registers. And this time, I'm no longer using EIP, EBP, and ESP. So see, I get this error saying invalid register EIP, EBP, and ESP. Reason being because I'm using it on a 64-bit. If I want to use it if I want to use EIP, EBP, then I have to use that M32 in order to have been executed on a 32-bit. So here in this case, I'll replace this as RSP, RIP, RSP, RIP, RSP, RIP. Okay. So I have bunch of things over here. The instruction pointer is at some location, and RSP and stack pointer both have been at some 60 and 70 because I assigned a breakpoint and it started taking in some values, and that is the reason both stack pointer and base pointer are at a different location. Now let's do disassemble. And here we are. So here is this It is subtracting the base pointer with the with our I did use stack protector, yes. And then we are calling this copier function, and somewhere in my stack I should get this value, and I should also be getting, if I continue this execution, I should also be getting the A's in my stack. And if it is happening, it means that something is going on in my stack and it is exceeding that particular value. So here, let me do this command this time. Rather than using single instruction, continue command will continue to the next breakpoint. So I'll use this command called continue. And if you will see that now it has copied this A. If I use just single instruction, then in that case, it will just go to next single instruction. But continue command will continue to the program flow till the next breakpoint, which I had assigned was B5. So it continued, which is copying the contents of this string, which I passed in the argument to this buffer location, which is having these 10 values. So here in this case, if you see that copier function is repeated 21 times at this test code. Now let's do this again, x32x and dollar RSP. I'm no longer doing ESP, I'm doing RSP. Here, if you will see that somewhere in my location should be this return address, which is 0xFFF1B5, which is the return address after the copier function is called, which was over here, which is stored on my stack. Let me do single instructions once again over here, which is still copying, and let's see if still I'm able to see the add. No, let me just do SI one more time and see if it gets updated. No, let's see. Okay, let's see. Now it should be updating. Somewhere in my location, it should be able to see this A's values, which I'm not able to see. 1 second, 64. Maybe I've executed the program somewhere. It has been lost. Let me just continue this. Yeah, I'm getting a segmentation fault, and I don't think I should be able to see now my contents. Let's do certain other things just to see if the values got updated or not. No symbol table or because of the segmentation fault. Okay, let me rerun this program once again and see. It's not executable. Okay, once again, I'll compile this test code gdb / test code. Okay. So I ran my program with many A's, and let me assign breakpoint at 5. I'll continue this. It will copy 48 times. Let's see. Values. Register RSP. Because it happens in one click of a second, and then it starts, as I mentioned. If I skip that particular step, it will just, I'm not able to see the contents. So my RIP is at 179, stack pointer is at 20 and 40. Let's see, my buffer is this. And let's see my address, just looking what exactly the buffer contains. Right now, it has not been updated. So that's the reason all of these are some random values. Now I did single instruction and let's see if this gets updated. So far, it is still the same. And let's see now if it gets updated. So I'll continue this. I have, yeah, so see over here. Now the buffer contains 0x41 in all of these locations. This is the hexadecimal value of A. That is the reason PX buffer value contains all the A values. And now let's check if what exactly the stack does contain and if these values are getting updated or not. So see, now I can see that starting my stack pointer position, which has been listed from DF20, it started getting updated. These F4141 value, if you will see, all of these are these A's values which gets updated. And as soon as I will do a single instruction, I will get a segmentation fault saying that that it is no longer available. So let me do an SI and see the program terminated with signal version and segmentation fault. The program no longer exists. So this means that this GDB is one of the tool we can actually see the contents. If it is being modified, we can check if the function call is rather than going to a specific location, if it goes to some other location. Here in this case, it is just changing the return location position to 41, 41, 41, 41. So everywhere these A's are written rather than being executed or returning to the return address, which has been specified. Is everyone following up? Does it make sense? What exactly happened in this case? Okay. I'll do one more thing that I'll not use stack protector this time. And I'll just run this, but I'll just use this -g command. And in this case, you will see that the values will not be updated. This is because the canaries are being enabled, and canaries are a tool so that you can restrict the program not to write the values where it is not permissible. So if I disable canaries, which in the previous cases I was able to override the values. But in this case, when I'm just running this program without disabling with stack protector, which means that the canaries are enabled, which means we would no longer be able to write the content. Then we will see how exactly if the GDB would be able to tell us if the values are being changed or not. So let's see. Now let me again do this test code and list breakpoint at 9. I'll run and with again with a lot of A's. If I run with 10, it should work completely fine. So let me just run with small 10 and then just assign breakpoint 5 and let's continue. This is copied to a single instruction, continue. And see, I get done, inferior 1, process exited without any errors. I can check the contents. I should not, I don't think I would be able to see because now it has come out of the program. So yeah, I cannot see because it has been executed. So let me rerun again this program. And this time, I'll put 9 and then I'll run this time with more A's and see. Let's see if the contents are being copied. Continue. So it copies 77 times, and str copy, I'll do single instruction maybe 3 times. It's still copying. I'll do info locals, and this is the buffer, only buffer value is present. And then I can check the contents of my buffer, which is not been updated. Single instruction, again, I'll see if the contents, let's do one more thing. Okay, now it has exited. Sorry. Yeah, so see over here, 0x repeats 30 times. Here in this case, if you will see that even though the stack protector was enabled in such a way that it was not able to write these values of A, which should be 0x41, it was not able to insert that value, and we were just getting 0x0. So the values were not updated at all. So the stack pointer, remains same without being values, which were updated. I'll again check this command just to see. Sorry, yeah, these are still depicting the same. So we were not able to change the values. The values were not updated at all. We can check some of the things. I should have checked the return address and other things. But this time we were not able to update these values. So now do you understand the difference between stack protector when we use stack protector versus when we do not use? Then in that case, what happens? So here, let's do one thing. In our lecture slide, over here, so the defense mechanism that is introduced in Canary is the utilization of canaries, and how canaries actually work. Let's see. So when we were calling that function, that example one code, you might have seen that if the function was being called, the value was just 0x10, 10 bytes, which in this case is like 15 values were just getting updated. So we subtracted 0x10. And if we just run this program without stack protector, then in that case, or if we do not have canaries being enabled, so canaries is a phenomena that you can introduce some pseudo random content which is taken from some arbitrary location, and you perform an XOR operation to verify whether the content has been replaced or not. And how exactly this works is, just quickly, I'll summarize that any compiler above 4.4.5 do have this stack protector being enabled. But if you want to disable your stack protector, you can just use fno command. And all these commands were listed in the tutorial. So if you can go back and run these certain commands. So fstack protector is enable enable these canaries. If you want to disable the canaries, you will just use fno, no stack protector. So how this works is using canaries, and canaries, what it does is that, so when you see that base pointer and stack pointer are getting updated, our stack pointer gets moved to a certain location, and before going to the next function call, a return address is stored. And that return address is the return address in main, which is just after a specific location, which in this case is just after the scan, which should be the return address. So what we do is that we introduce this canaries just before and after that function call. And what exactly it does is, it does three things. This particular slide will tell you. So what it does is that it takes some contents from some location, which is at this location. So GS20 basically says that there is some register EAX. Go to this arbitrary location, which is this GS segment, and whatever is the content from there, store it in EAX. That's step number one. After that, what you do is you move the content of this EAX to your stack. So this is your stack, and you move the content of this location, which is copied from this arbitrary location, to this stack pointer. After this, you XOR the content of EAX and EX, which means this would be 0. So you XOR. So this is before the function is being called. And after the function is being executed, you verify whether the canaries has been changed or not. And for that, what you do is you take the contents from the stack and you put this in this EDX register. So you put this in EDX register. And what you do is you verify the content which was originally shared over here, which was GS, and this content, which is EDX, if they are same or not. If they are same, which means nothing was changed, nothing was modified. But if EDX XORing EDX with GS returns some different value, which means that the content was modified. So with this, I'll finish the lecture, and we will talk more on canaries. What I want you to do is practice all these commands that I have shown today. Look back to stack, how values are being updated, how exactly these commands are written, what exactly these are done. Because in your lab number 3, there is one exercise on taking one code and just showing the contents. So make sure you go through some of the tutorials that I have listed. Any questions, I can answer that. Otherwise, I'll end the class.